Welcome, everybody. You're joining us today for Next Generation Optics Software Trends in Technology. This webinar is sponsored by LightTrans International GmbH and hosted by us at Photonics Media. So today you're going to be hearing from Frank Wyrowski, who is president of LightTrans International. He co-founded LightTrans in 1999, as well as Wyrowski Photonics in 2014. Since 1996, he's also worked as a professor of technical physics and a head of the Applied Computational Optics Group at the University of Jena in Germany. He focuses on developing fast physical optics solving techniques and on software for modern optics and photonics design. His current research and development has centered around light guides for AR/VR applications, light shaping, interferometry, fiber coupling, and much more. So in this webinar, he's going to be talking about optical systems modeling that applies ray optics within a physical optics software framework. You can ask questions or leave comments at any time. Just type those right into the webinar chat box. If we don't respond to you today during the live Q&A, we will send you an email later. If you have any technical problems during the show, like you can't hear or you can't see the slides anymore, please try leaving and coming back. That usually fixes it. But if it doesn't, don't worry, this whole session's being recorded. It's going to be on the Photonics Media website very soon, and you won't have to go look for it. You're going to get a note by email afterward letting you know when it's up. So that's all from me for now. I would like to welcome Frank Wyrowski.
Yeah, Sarah, thank you very, very much. And it's my pleasure to present my thoughts today. And first, let's fix that we have a good start. So everything's fine?
Yes.
Okay, cool. Yeah. The title is Next Generation Optics Software, and what I like to do is I like to share with you a little bit about my thoughts on this topic. And it's also the story I like to tell you is also a little bit the story behind the software Virtual Fusion. Okay, so the content of the webinar today is very simple, 3 parts. I like to introduce about what my thinking is about the unified approach in optical modeling. Then let's go into some further considerations on physical optics modeling, but here's the relief. It's almost equation free. That's possible. You can talk about physical optics without equations almost. And then at the end of the webinar, I like to give some examples, some in the talk, but much more in the follow-up material. Depends a little bit on the time. Okay, good. Yeah, let's start with the introduction to this unified optical understanding as I think about it. And we have, I just need to put a little bit this away from the GoToMeeting. So now. Okay, so when we talk about this, then I just like to introduce in the very beginning a little bit about Virtual Fusion, the software. We started the software in 1999 as a quite clear diffractive optics software at that time, and then we did something, some trials in this direction, some trials in this direction, but in the recent 5 to 6 years, we got a clear orientation in the direction of fast visual optics as a physical optics software. And the term fast is related to what you also call fast Fourier transform, to be, if possible, linear in the number of sampling points. So when we talk about fast visual optics, it means we aim as whenever possible. So of course not always possible, but whenever possible, we aim to get a numerical complexity linear in this number of sampling points. That's the reason for calling it fast visual optics, which clear reference to fast Fourier transform. Now, all examples in the talk are done with this software, and the ideas of this software, this is also the ideas I like to present here in this talk. Now, the whole thing is in steady development. It's still a long way to go to come to all what I have in mind on that. But we are quite on a good way, and I'd like to talk about you today about what's our starting point and how we think about these things and what is a bigger perspective. In 1998, there was this book, Harnessing Light. That was really a very, very interesting book. For me personally, it was also interesting because it was also the time when I got my professorship here in Jena. And when I published together with Jarek Turun the book Diffractive Optics in 1997. So it was quite a time to think, what's coming? What's the next? And I was very impressed by this book and by this clear understanding that photonics is an enabling technology. It's not a big thing like car industry, like chemistry or electronics. It's an enabling technology. And this understanding of enabling technology is also continued by the same committee, by the way, Harnessing Light Committee, in 2013 by a next report, Optics and Photonics, Essential Technology for US nation in this case, but for our nation, Germany also. That's for all nations, I would say. The most important thing is that it's enabling technology. It's enabling technology in more and more applications. And of course, if you look into all the applications, I just took them from the table of contents of this book. So different areas. Then of course the question appears, and it appeared for me also some time ago. What does that mean for optical modeling and design? What does it mean if optics and photonics is an enabling technology? What does that mean for modeling and design? Not to talk about fabrication, measurement, and so on, just for the field I'm concentrating on, modeling and design. So what is the need which comes in optical modeling design for that? If you understand optical modeling and design as the three-folded thing, source modeling, component modeling, and detector modeling, then one thing is very, very clear to me, that optics, if it's an enabling technology, requires, of course, a maximum flexibility in source, component, and detector modeling. That's completely logical. If you are not super flexible, then you always have some limitations, then you cannot do that. And what does it mean if you put these things together? Then you have system modeling. And system modeling means, of course, you use some sources, you use some components, you use some detectors, and you somehow like to calculate what happens if you switch on the sources and the light propagates through the components, and you measure something at the detectors. So that's what we like to do, mainly also in a non-sequential way. So really in a real life situation, I even put here the arrow back to the source for the self-mixed interference, which is gaining momentum in applications nowadays. So that means this kind of situations we like to do. And then if you like to do this, and I like sometimes to use the word digital twin, at least here for optics and photonics. So if you like to do that, then of course the question appears, what are the theories and the technologies we can use, which we can use for modeling and design? That's a question we have. And we like to be very flexible because we like to do it in the sense to be fit for enabling technology, optics and photonics. So how to make optics and photonics from a modeling point of view fit to do what is an essential technology for our nations. Okay, on the one hand, we have general optics. General optics is a really well-established technology which has a long history. And I would say with Fermat in the 17th century, we have a clear mathematical compact description of that. And then I must make a break here, otherwise the scale is not good enough. And then with a quite new technique, young one in comparison to general optics, we have physical optics, which is summarized in Maxwell's equations. So we have these two parts. And if you look into the state of the art general optics, optical modeling and design, then of course we see general or ray optics is very, very powerful in optical modeling and design in a wide range of applications. There's no doubts about that. I like to mention that also in lens design, which is the most important application of optics design, of course, there we have already a connection to wave optics. If you think about, in particular, me as a Yemen, there's somebody come from Jena, I should think about Abel, and then I know there's a very special connection in lens design to wave optics by the pulse space function and modulation transfer function calculation. So there is already something beyond wave optics in lens design, which is well established, and there's quite some books about that. And but anyway, general optics dominates optical modeling and design in theory. praxis, and software products. That's a matter of fact. On the other hand, and that's also a fact, physical optics provides solutions beyond general optics. So it gives us the idea, the expectation to have a higher flexibility because, and that's a matter of fact, physical optics includes general optics. That's just true. And here's just a picture from 𝗃𝗲𝗀𝗀, page number 2. And that means we have the situation that we can say physical optics includes ray optics. And physical optics by that is an extension of ray optics. That is exactly what we like to have, to be so flexible. But on the other hand, this fact has not a strong practical consequence yet. In fact, we don't feel it too often, right? If you look into books, then we have ray optical books, very good ones. We have physical optics books, very good ones. But the connection between general and physical optics is almost not visible. They have a different language, even they are all English, but they have a different language to discuss things. Sometimes there's even no relation in formulas, so it's really not together. And so there's no surprise if even the theory is not together, that then the software products are also not together. Because we have ray optics software, often called ray tracing software, for lens design and lighting, of course. And we have also a lot of physical optics software, special ones, FDDT, FEM, and so on and so on. They are all great, but alone, at least for system modeling, they are not suitable. They are good for special tasks, nano optics, for example, coating, of course, but as a system model, no. And also the connection between the ray optics software and the physical optics software, there are some connections, but it's really not convincing. So it's quite of data interface, but not really a conceptual interface. So we come to the conclusion that the status quo is optical system modeling relies on ray tracing software. That is just the situation we have. But that is not good for our goal, because our goal is that as an enabling technology, we must be much more flexible. And this flexibility cannot rely on ray optics. And we know it from our customers, I know it from my colleagues, I know it from my research. I'm sure that here today listen a lot of people who know this kind of being in the bubble of ray optics and have some difficulties to come out. A little bit add on here, a little bit add on here, but there is no unified concept. And that's a problem. And that's a problem to be fit for the demands we have from the industry as an enabling technology. So that means, in summary of this situation, we have a current situation, general and physical optics coexist without a powerful connection in theory and praxis. Some design tasks apply specialized connections. I mentioned the PSF, MTF. But anyway, it's mainly a coexistence with some kind of connections. Our demand would be to have a seamless transition between geometrical and physical optics in theory and then also in praxis. And this demand you can hear quite often. The question is here, is that a reasonable demand? Makes that sense at all? Is this a good question to do that? The problem is the light representation in physical optics are electromagnetic fields. It means we have electric fields, we have magnetic fields, and together with electromagnetic fields. Light representation in general optics are ray positions, ray directions, the OPL, the optical path length along the rays, and at least in non-imaging optics, also the flux. This is a typical description. If you have this kind of typical description, fields here and ray parameters here, then the question for a seamless transition is meaningless. You cannot have a seamless transition between field description and zwischen rays. That is somehow a principal problem. That means this is not a good question. To get into the future with this question, it's a non-starter. It means we must formulate our objective in a different way. Otherwise, we are already here at the end of the story. What we need to do is we need to make a big step. We must say the part of ray optics must be generalized to electromagnetic fields. We must use in the part we have to have a seamless transition. We must have a step there where also electromagnetic fields are used. We cannot go into unification into a subset. So we must go to the general description. That means we must take the same description as in physical optics in general. That sounds crazy to you, maybe, but that's not my idea. That's the idea and the proposal by Born and Wolf. That was already published in the famous book Principle of Optics on page number 125. Here's a citation, or I say it now. We need to identify that part of physical optics which deals with the geometrical laws relating to the field vectors. And that means we need to have a physical optics generalization of general optics. Here's a book, here's a page, here's a citation. You can read all of that, of course, to get the material, but it is, however, possible, and from our point of view, quite natural, to extend the meaning of geometrical optics to embrace also certain geometrical laws relating to the propagation of amplitude vectors E and H. That's exactly our thinking. That means we must generalize geometrical optics by including the fields, by formulating it for the fields. That means what we do, we follow Max Born's and Emil Wolf's advice. And we refer to that, or I started to refer to that as a geometric branch of physical optics. Whatever that is, we need to discuss, but that's a goal. That's a goal. If we have that, then we have the same field description here and here. Then at least it makes sense to look for a seamless transition. Before it even makes no sense. Now we still have not solved it, but at least we know what we need to do. We need first to generalize geometrical optics, and then we can find a transition. So that's the goal. It means our current situation is not changed, but our objective changed. The seamless transition we are looking for is not the seamless transition between physical optics and geometrical optics, but the seamless transition between physical optics and its geometric branch in theory and praxis. I always emphasize theory and praxis because it makes no sense whatsoever to try to develop a software if you have not the theory to do that. Okay, so theory first, and then you can derive the software. What we expect when we have this kind of thinking, that's not a proof, but that's just an expectation. It's a hope. That the geometrical optics itself follows from the geometric branch of physical optics by restricting to ray parameters. So that's what we have. So it means the thinking of ray optics as subset of physical optics is replaced by saying you're looking for a geometric branch of physical optics. And if we have that, we need to find it. But if we have it, then we can extract ray optics out of it. As I like to call it, a special mode of operation of physical optics. So ray optics should become a special mode of operation of physical optics. So that is a situation. I feel that this is a major trend in the development to become fit for the demands we have in the optics and photonics community in the modeling and design part. Not to talk about all the other things, but the modeling and design part. Seamless transition between physical optics and its geometric branch, and to understand geometrical optics as a special kind of mode of operation then. That means instead of having a coexistence between physical optics and geometrical optics, I predict that in the future, geometrical optics and physical optics come much, much, much closer together and finally become one theory with different aspects and different modes of understanding. But we will overcome, I'm sure, we will overcome quite soon this kind of coexistence without connection, and we come to a unification with strong connections. And I like to say that, of course, our software development is based exactly on this thinking. We try exactly to do that. It's a foundation what we do, and it's a direction for the further development. So that's the situation we have. Now, of course, comes a big question. What is that? What is this geometric branch of physical optics? How to formulate a theory which connects the general physical optics and this geometric branch? So that's, of course, an open question now, and we need to answer. So I come to the certain considerations now on physical optics modeling. How to define this geometric branch of physical optics? For this, I go back to ray optics. Let's remember, ray optics is based on Fermat's principle if you like to propagate light. In homogeneous media, now I say here, that means glass, plastic, vacuum, whatever. So no components. So light propagation is in Fermat's principle here. And in physical optics, light propagation is Hologens principle. I use these two terms because you know both, right? Fermat's principle, Hologens principle. Fermat's principle you learn already in the school. If light is somewhere here, there's a point where light is, then there is a ray and it's straight going to the next point. A light here goes straight to the next point. So that's Fermat's principle in free space. So there's nothing in between, right? So that's Fermat's principle. The essence of this is that you have a point-wise connection. 1 point here gives 1 point here. 1 point here is 1 point here. That's what we call point-wise. A multiplication is also point-wise mathematically. So it's a point-wise operation. Whereas the Hologens principle is 1 point gives a spherical wave. Another point gives a spherical wave. That's an integral connection. That means from this very basic understanding, we see that the fundamental of general physical optics is an integral behavior, whereas the geometric laws is a pointwise behavior. So I come to the conclusion that it's probably a good idea of first numerical complexity. Numerical complexity here is integral is n to the power of 2, so n sampling points, integration n to the power of 2, whereas of course pointwise is linear in n. So that's also cool. And that's, by the way, a good reason why ray tracing is often faster than physical optics. If you do ray tracing or if you do Hologens integral, then it's much, much, much faster because this is quite some difference here. Okay, good. So now it comes to the point that I say it's probably a quite good idea to define the geometric branch of physical optics from this here, but just to put the rays away and take the fields. So take the fields and make a pointwise connection with the output. Don't think about rays now. The only important thing here is that the field in the input and the field in the output at different locations is related pointwise. 1 point, 1 point, not 1 point, a lot of points like Hologens, but 1 point, 1 point. That's just a proposal. That's just an abstract definition power. Okay, so that means this is a quite straightforward thinking to say the geometric branch of physical optics is defined like this. And that would mean that the geometric branch is that part of physical optics where we have pointwise physical optics operations. We do physical optics, but pointwise. And you will see that does not mean it's approximated. It can also be very much, it is rigorous. So it depends on the domain where you are, but we will see later very clear. So it means in a more abstract way to formulate it, in the general way, physical optics is an integral connection between the input field and the output field. So it's an integral. Whereas in this subs field, in the geometric branch, we have a pointwise operation. So one input field at one value, get a matrix on it, and comes an output value at a different position. So, and this can be done. It's sometimes also even in extended ray tracing, I would like to call it, it's already done. So this is not completely new to think in this way, but I like to continue this in a systematic way. So I like to do it not ad hoc, but I like to do it in context. So that means I say, let's define the subset by this kind of pointwise operations. So we have the Huygens principle and we have this pointwise connection. And now, of course, the question appears, how can that be? How can this be sometimes this? So in some situations where geometric optics is allowed, this geometric branch is also allowed. So let's have a little bit more careful discussion about this, because we can learn a lot by a careful discussion of this. Now, let's do that as it was Huygens principle for homogeneous isometric media. It means if you talk about system modeling, we talk about all these connections here, so all the space in between, but also, for example, in a lens, inside the lens, you also have a homogeneous medium. So we talk about propagating from one source to a component, or from a component to another component, or from one surface to another surface in a lens. So that is what we are now talking about. So, and the Huygens principle, which is our starting point now, has its rigorous formulation for Maxwell's equations by Rayleigh-Sommerfeld integral. So that's a Rayleigh-Sommerfeld integral. Just to give it here, we don't need to discuss in detail now. And this is the rigorous formulation of Huygens principle per component. It's possible per component for all 6 field components. So there's no scalar approximation, nothing. It's completely rigorous here do it for 6 components. This kind of propagation is a key technology in physical optics modeling, of course. So I do it here now in this kind of description. Here I say X domain is a space domain. And I can propagate a field in one plane to another plane by this integral. If you look into this integral, or if you would look in this integral a little bit more, then you would see it's in the form of a convolution, a mathematical convolution. That means you can use a convolution theorem and formulate it as a product of the Fourier transform of this. And the Fourier transform of this, that's a Weyl representation, by the way. The Fourier transform of this is this. That means it's 𝘃𝗲𝗿𝗀 factor. That means in K domain, the Rayleigh-Sommerfeld integral becomes a simple product. So Fourier transform, product, Fourier transform. Now, you see, I have here points around the P. That means it's a pointwise operation because it's a product. The product is pointwise. One value, product, next value, and so on. It's a pointwise operation. Of course, the Fourier transform is an integral operation. So in the sense of a pointwise situation, we don't have any change. So we don't have any change, but we have here a pointwise operation, and here we have an integral, here we have an integral. But we have already an advantage because of the complexity. The complexity here is n to the power of 2 is an integral. And here the complexity is linear in n. Why? Because thanks to the mathematicians. The mathematicians have given us a gift of the FFT, the fast Fourier transform, which is linear in n. That means when we go via the Fourier transform, we have linear n, linear n, linear n, which is very often much, much, much better than to take n to the power of 2. Not always, there are some special situations to be discussed, but in general, I prefer to discuss free space propagation via the K domain, which is of course also often called the spectrum of plane waves. But the spectrum of plane waves is the K version of the Rayleigh-Sommerfeld integral. Okay, good. So that's the situation. Now, question: how can this become pointwise? Because that's what we are looking for, right? We are looking for the subset of pointwise propagation. And in free space, at least we should be able to solve it. If you cannot do it in free space, then we can forget it, right? So how this can become pointwise? The answer is trivial. If the Fourier transforms becomes pointwise, that means this kind of stuff can only become pointwise if the Fourier transform itself are not longer an integral. That means a pointwise physical optics propagation in a homogeneous media can only be obtained if both Fourier transforms become at least approximately pointwise. And this pointwise Fourier transform is absolutely a key technology for our type of physical optics modeling as we do that. It's a key technology we have developed in the recent 5 years. And I give you an example. Let's assume you have a spherical wave and you illuminate a mask, an amplitude mask, simple amplitude mask. That's a house. And then you have the house here. And then you illuminate, then you have here the amplitude behind the mask. And then you like to do the Fourier transform, and you calculate the Fourier transform. So let's do that. But let's do it for an increasing NA. So the angles becomes larger and larger. That means the wavefront becomes stronger and stronger, with strong remains high NA. And now we do that, and then we calculate the integral Fourier transform. And let me see, if you do the integral Fourier transform, then with increasing NA, here it's typical Fourier transform, right? Here, Naya, and here, and now you see it starts to become a mapping relationship. This one and this one looks even identical. And this one is a mapping behavior. And so that means we have a situation where we can compare a pointwise Fourier transform and a fast Fourier transform. So we developed a pointwise Fourier transform. It's in fact to apply the stationary phase concept to the Fourier transform itself. And then you can derive that. And then we show the results. So here on the left side, you see the pointwise Fourier transform, and here you see the FFT, NA0, so plane wave, just the mask. So it's completely, the PFT, the pointwise Fourier transform is completely wrong. Now we go up with the NA, more and more wavefront, okay? So still wrong. And now you see it becomes quite the same. But here we need just a few sampling points because it's a linear operation. And here already more and more. So you see, we have a situation where the FFT becomes approximately more and more. So here's the FFT. Also, the numerical effort becomes higher and higher. And here's the PFT, which is constant numerical effort. I cannot go into the details of that, of course, but it's a matter of fact. And you see the error goes down quite fast. And then the PFT works. That means, just as a fact here, we have the following situation. The pointwise Fourier transform is valid for field components with sufficiently strong spherical and aberrated wavefront phases. The validity of this sufficiently can be calibrated. So that can be automatized and can be estimated to make a switching between the integral Fourier transform and the PFT. That enables a seamless transition between the integral and the pointwise Fourier transform in physical optics modeling algorithms by pure mathematics. It has nothing to do with any physical model. It's just the accuracy of the Fourier transform, pure mathematics. That's, in my opinion, extremely important. And there's another thing which is good, that is the PFT, the pointwise Fourier transform, and the FFT have a numerical complexity linear in n, both. The FFT because of the mathematicians, and the PFT are because it's pointwise. So it's linear by nature. However, the number of sampling points, n, in the PFT is significantly smaller. Because in the pointwise Fourier transform, you don't need to sample the exponential factor of the wavefront, which is really a killer in FFT applications. Everybody knows who's doing physical optics. That means if you have typical numbers of FFT from 10 to the 6 to 10 to the 8 to 1,000 times 1,000 or 10,000 times 10,000 pixels, then you have in the PFT just 10 to the power of 2 to 100 to 1,000, not more. It means here we really talk about several magnitudes, orders of magnitudes, which is very, very essential to be fast. So linear is fast already, but smaller n is even better. Now, we come to the situation that if you now say, okay, we have a free space propagation. Free space means we start somewhere, Fourier transform, then the P, pointwise, and then back. And now I first introduce here a simpler diagram here to do that a little bit faster. Now let's talk about this free space propagation. And I also like to introduce here a little bit a different scale here, because I need to urgently X and K domain. So this is my illustration for the rest of the talk. So I have here my source, my detector, and then I propagate from the source. I have a Fourier transform. I go to my P operator in the K domain, and I go back here. So this here and this here is now this. Just a 2D description and this diagram description. Sometimes the one and the other one is more instructive, so I use both. And now it's clear. If I have a pointwise propagation, then both are pointwise Fourier transforms. This was very, very nicely discussed in this paper here, and where also the GUI phase shift and so on is included, because we can show that then also GUI phase shift is included in the modeling. Still, it's pointwise, so it doesn't matter. So that means the key here is if both Fourier transforms are pointwise, then we have a pointwise propagation. And by the way, I'd just like to mention it because it's so cool. If the second Fourier transform is integral, then you have the Debye integral. If the first one is integral, then you have the far-field integral. So that means this kind of concept of selecting the pointwise Fourier transform is not only good to have a pointwise modeling in one step, but also to discuss so-called diffraction integrals. Now, what do we have from that? Now let's go to system modeling. As long as we take, let's assume we take for component modeling, we take the finite different time domain technique. Let's assume we can take also FEM or FMM or whatever. So let's assume we take this kind of technique, which is definitely not pointwise. Then even if all this here is pointwise, Fourier transform pointwise, the P is pointwise anyway, Fourier transform. So all is pointwise, that doesn't help me. Because here in the middle, we have the weakest point for the pointwise discussion. That's FDDT, which is integral. So over. So we cannot have a seamless transition to physical optics modeling in a pointwise way when we restrict to just such kind of excellent solver. This is we have no any kind of forward way because the whole thing is still not pointwise. So it's not a seamless transition to any kind of pointwise thinking and later to a geometrical optics mode of operation. So that doesn't help us. So we must do the next big step. The next big step to be able to do this is we need to connect a lot of solvers. One solver is not enough at all for a lot of reasons. But in particular, because with one solver, it's always an integral solver. A universal solver must be an integral solver. So that doesn't help us. But if you take a lot of different solvers, then we can hope, of course, that some solvers are pointwise in the K domain or in the X domain. And then if you connect them, then the whole modeling could become pointwise in some situations. And we will see quite in a lot of situations. And then if you have this situation, and you will see we have them, then we can just go into mode of operation of geometrical optics. Everything is fine. So that means we have the following thing to do. We first have to introduce a lot of solvers. We need to connect them. And then we need to see how to connect pointwise solvers. And if then in addition also all pointwise, all Fourier transforms are pointwise, then we are doing modeling in the geometric branch of physical optics, and then we have a connection to geometrical optics as a special mode of operation. So that's a story. It means then these are just my illustrations here. You know them already now. So I have here my modeling diagram, propagation here, solver here, detector. So we will see that a little bit more often in the examples. And here the other one. So I use these two ways to illustrate modeling situations. Now, if the connection of solvers is a key technology for physical optics system modeling, not just because of the pointwise stuff, but also for being fast, because the pointwise solvers are always faster than the integral ones, right? So to be able to do that, we need a lot of solvers. I cannot go into the details of this in this talk. That's completely too much, but it looks like that. We have a lot of different solvers. You can just go through the literature. Always smart people having new ideas. And all these solvers are welcome. We love them. Any solver is cool. Okay, FEM, FDDT, and all the other stuff. Any good new idea for a solver of a specific thing is welcome and can be put into this context. In Virtual Lab already, okay, here are some names. I don't go through them now. I'd just like to mention that LPIA stands for Local Plane Interface Approximation. It's our working horse. So here are some references. So I just mentioned this because I use it quite often in the examples. And so we have the situation here. We have different solvers per component. And in our software, we don't have FEM, FDDT. We rely on FMM mainly, actually, at least. So we have this kind of solvers, or at least in the year they will add, which is still missing. But most of them we already have. So this kind of solvers now can connect it, and we do it in a way that each component comes with a solver. So for example, A lens comes with this solver. That is on the solver tab. A grating comes with a 𝗲𝗲𝗀𝗀 method. That comes with a solver. So you take your component and you have your solver. You don't need to think about it. It comes together. And the propagation step, which is propagating the light to your solver for the connection of solvers, that is done by the Fourier transforms. You can do it by adjusting the two Fourier transforms, pointwise, not pointwise, and so on. And typically, you can do it automatically. So that means the software decides for you to do the right thing. We're just developing for the next release a quite nice control panel for that, so that it becomes very transparent if you do a pointwise or an integral modeling, or if you like to use an automatic one. So it means we have the situation. We have source modeling, we have detector modeling. I don't talk about this today. Then we need a pool of solvers, and then we can connect them. And that's the basic idea. And if we are working in this pointwise subset, and the Fourier transforms are all pointwise, then we are in the subset of the geometric branch of physical optics. In practice, that means you build your system by selecting and positioning your components. The components come with a solver. You select your Fourier transforms, or you leave it to the software. You customize your setting, or you leave it to the software. And then the software evaluates all relevant light paths through your system based on the 3D configuration. And then the software knows and evaluates all the light paths through the system by connecting the solvers in a non-sequential way. That's it. That's all. The more solvers you have, the better. The tricky thing is, there are a lot of tricky things. The tricky thing is to have the connection technology. The tricky thing is to have a light field representation, which includes all this different type of mapping style and so on. It's a hybrid sampling situation and so on. So there are a lot of things, interpolation, a lot of technologies included. But the basic idea is that. So that is what we are doing. And then you can go to a geometric optics modeling. And I like to come now to a few examples. I have still some 8 minutes or so before I like to go to the question and answer, and then we can put more examples in. I like to start. I have some examples. So let's start with the lens modeling, because that is definitely the most important thing. I like to show you where we are now when we talk about lens system modeling. In lens system modeling, we have typically lenses and apertures and mirrors. The lenses and the mirrors are modeled by LPIA, also in physical optics. That's very accurate technique, very, very accurate technique. And truncations are done by truncations. If you have very small, teeny pinholes, okay, then you need a rigorous solver. But typically in lens design, we are just cutting the light, right? We crop the field. So that means we have these two things, and they are combined. So we have a free space propagation. Then that's X domain, red is X domain, pointwise. So you have a truncation, you have this modeling of the surface, then you go back, up, and so on, and so on, and so on, and so on, till you are ready. Then you are somewhere, for example, in the 𝗃𝗃𝗀𝗀, or somewhere behind your lens system, doesn't matter. And then you propagate to your detector. So that's the situation. And they're all Fourier transforms here. Now, the detector, I just like to mention it. I discussed as parallel planes, but in our concepts, there's no change. When we go to tilted planes, it's also possible. That's just a modified operator, a pointwise operator in the K domain. So tilt is also included. Now, what is the standard ray tracing approach? That's this. From a physical point of view, is all Fourier transforms are pointwise. Then you go with your spherical wave through, and then all is pointwise, all is pointwise. And then you are at your result, and you get your mapping result. And the mapping result is your dot diagram. That's all. Okay, so that means your mapping result is a dot diagram. And if you have all these mappings and you connect them, then you get your ray tracing picture in 3D. Now, we know already here the last Fourier transform here. That is not a good idea. If it's a focal plane, it's not a good idea to do by a pointwise one. But okay, that is to go to geometric optics. But here, from the accent pupil to the detector, to use pointwise Fourier transforms here is not always a good idea. In particular, the last one not. in the image plane, right? So this is typically done by a Fourier transform, by an FFT. The first one, often not, because often in lens modeling, the 𝗣𝗲𝗀𝗀 integral is used, and then it's just one Fourier transform, which is sometimes called FFT technique, but in fact, it's a 𝗣𝗲𝗀 integral. Now, if you have a laser beam, then you have a different situation. If a laser beam, then it already starts here to have trouble, because a laser beam in its waist does not allow a pointwise Fourier transform in the beginning. Here we have a pointwise Fourier transform already in the beginning. For spherical wave, that's fine. But for a Gaussian laser beam, that's not okay. So it means that makes it trouble to start ray tracing for a Gaussian beam, right? Because that doesn't work. It doesn't start. So you need to start with a Fourier transform, with the integral one. Then you go back. Maybe this is already pointwise here. If you are Rayleigh distances are large enough, you have some 10 Rayleighs or 20 Rayleighs, then you can already do a pointwise Fourier transform. And then you go through, and then the same. If you have a paraxel field, then typically all the Fourier transforms must be not pointwise, they must be integral ones. Then you are in somewhere in laser optics books or in Fourier optics books. That's the situation, right? If you have a paraxel system. And then often LPIA is replaced by the thin element approximation, because that's enough for paraxel. LPIA is a generalization of the thin element approximation. And if you now go through this, then you have a paraxel lens system modeling. Then you are very much in Goodman's book Fourier optics. And if you have this kind of situation, then you can even approximate the lens by quadratic phases, and then you can even combine all of this. That's super cool. By one step, that's a Collins integral. That is for paraxel lens system modeling. You see, I go through the standard lens design till the Collins integral just by changing my Fourier transforms. I think that's a quite powerful concept. And so, in general, if you don't know what the lens is doing, then take automatic one, and the software decides for you what kind of Fourier transform is to be selected. I'd like to show you an example. It's a laser diode coupling into a fiber. So that's a quite ugly laser diode in blue, 405 nanometer, very, very astigmatic. And we like to couple this light into a fiber. It's a monomode fiber with 3.3 micrometers. So we like to have a Gaussian beam here, but we don't have a Gaussian beam here. So then we do a freeform design. I cannot go to the design now, but the design is done also by physical optics thinking and inverse design approach. It's not parametric optimization, it's a direct approach, including light shaping. And so we have two freeform surfaces, one here, one here. We can do, of course, ray tracing. But you see here, we can also do, of course, physical optics modeling. And then we get here a nice spot and get a very high coupling efficiency in the simulation. Modeling here, yeah, as I described before. Here, the laser diode first Fourier transform is an integral one, then pointwise, and at the end, again, integral one, because we're in the focal plane. This is now shown here. It follows by the automatic setting also. And then here you see the different fields. Here is the output field of the laser diode. Then it propagates a bit, becomes more symmetric. Then it's shaped to a Gaussian profile. And then it is focused to a Gaussian spot. So that is what we find then. Good. Another example for freeform, I also like to show you this, but no, I don't like to show you this. I like to show you one other example. Not easy, I take interferometry. So let's take a microson interferometer, because that's a very typical physical optics situation. So let's think we have here a spherical wave going through to a lens, beam splitter, and so on. Here we have a probe. The probe can be a plate only, or we have here some kind of higher part. Now, modeling, LPIA for the lens, clear. The plane interfaces are done by layer matrix. That's just coating stuff. The mirror also coating stuff. And here, the plate we are modeling by T. So we take these three solvers. And now we're propagating through it. It means we have here all solvers are in the pointwise domain. So we can do a pointwise modeling. if you just enforce point-wise Fourier transform. So let's do it. So we enforce point-wise Fourier transform. So we have a full point-wise modeling. And then let's first say we take distance 0. Then we get here at the detector, we get this intensity. You see there's even some kind of modulation because of the lens and polarization here. Very slight modulation. And then we take here now a little bit the height. Then you see very nicely a tilt. So we now do a tilt here and the height. So we do both together. And then we see we have the tilt from the mirror here, the tilt, and we have from this here, we have this interferometer. That's by a point-wise physical optics modeling. These things take seconds, not longer. Okay, just you do it and it's there. But of course, here we have some diffraction effects at the corners here, right? By the point-wise Fourier transform, I excluded them. Now, if I like to see them, I don't know, it's a non-sequential modeling. I don't know how to do that perfectly. So I switch to automatic Fourier transform selection. And then you get this result. So you see here, now you have diffraction effects. Here, point-wise, here, not point-wise. And the software decides if this is here, what you like to have or this. So it depends on what you like to see, right? And what you like to see in addition. And so these are just quite some situations. I have more examples. We can maybe discuss later about it. I'd like to come to the conclusion now. What are my conclusions for next generation software development? First of all, point-wise physical optics modeling must be included. That's a key. Then it must be an open platform for connecting many physical optics modeling techniques. Connecting solvers, rigorous and approximated ones, that's essential. So it must be a connecting solver platform, not just one solver. It must connect solvers, very important. The way optics must be understood as an easily accessible special mode of operation of physical optics. It is not something in addition, it's included. When we do point-wise physical optics modeling, it's just the same numerical complexity. We have n sampling points linear. There is no more effort if we do point-wise physical optics or wave optics. It's the same complexity numerically, so there's no difference. Maybe a little bit overhead or so, but that is not really a big thing. Another thing which is very important, where we need to work quite hard on it to achieve something here, it's CAD, of course, must be included for the components. That means we need to have a technique to combine solvers with CAD components. That's a little bit challenging, but it's a channel concept, which is also quite important to do. The modeling of the sources, the components and detectors, they must be really customizable. That's really important. It can be not a fixed software. It must be a customizable software, because that's the only way, in my opinion, to unleash the flexibility and the power of physical optics modeling. And that's very, very important. And I mean, the unleashing the flexibility and power of physical optics, I think that is exactly what we like to do, right? And I also like to emphasize, typically design in lens design is a parametric optimization. But I think we all feel if you do other things, then parametric optimization is not always the best choice, right? So it means in next generation software, we need also more and more alternatives, which using inverse approaches and other design approaches. So we also must open our mind for new types of design techniques. For example, diffractive optics, we do that, of course, already for some time, but there comes more and more. And also these new design techniques will and already benefiting a lot from the extended understanding of modeling. So I would say that's quite a good last say, unleash the flexibility and power of physical optics modeling. That is what is going around here, and where we will also, with our software, Virtual Fusion in 2022, go the next big steps. So thank you very much for your attention.
Thank you so much, Frank. Yeah, so we've got about 5 minutes to take a handful of questions. And if you haven't already, you can type those right into the webinar chat box. So my first question for you is, can you briefly talk a little bit more on paraxial lens systems modeling for a collimation system?
Yeah, if the system is really 𝗃𝗲𝗀, then you can make it faster. But if you do 𝗃𝗲𝗀 modeling, okay, our modeling lens modeling in general has no limitations, of course, right? So that means we can do 𝗃𝗲𝗀 or non-𝗃𝗲𝗀. 𝗃𝗲𝗀 optics in general don't know aberrations. So we have two things to understand. If you like to understand the lens system just from the functional point of view, if the collimation angles are okay, if it's really collimated, if the distances are fine, then I would say you can do a 𝗃𝗲𝗀 modeling, and that is a special mode of operation in our physical optics modeling. If you also care about aberrations, then you must go beyond that, and then you use the standard lens modeling we do. No, but it's always best to discuss that at a specific example. So you're welcome to send me a more specific scenario, always.
How does this technique work for a non-spherical surface system using, say, few conics and torics?
The local plane interface approximation works for all surfaces. So we even do it for microstructures, micro lens arrays, for diffusers, and so on. I don't see a limitation there. Also here, I would like to see an example, but I cannot see any kind of a problem here. If you talk about modeling, we don't talk about design, right? We talk about modeling. In modeling, I don't see any kind of issues here.
Can this approach? Yeah, go ahead.
No, always, I can just invite people, give an example, and then we can check that.
Yeah, and you can type that right into the chat, or you can email us at webinar@photonics.com.
Absolutely. Yeah, happy to answer this.
Thanks, Frank. Can this approach be extended to non-sequential modeling, for example, for stray light modeling?
It was non-sequential. I have also in the follow-up, you also will get. I didn't show a non-sequential example, but the modeling is non-sequential. The interferometer was non-sequential, by the way. Okay. So I also have an example of a ghost image, for example. And the stray light, yes. I also have examples of stray light modeling in the follow-up material. So stray light modeling is quite interesting, by the way. This can be definitely included. If stray light means stray light of the optical systems. What we don't do, and I don't see that we do it fast, that we introduce any kind of scattering from the housing. Okay. But I mean scattering of the optic components itself. For example, a stray addition to a point spread function should be definitely possible to do. We never did that before, but I don't see a big issue. I don't see challenges, but I don't see a problem to do that. Yeah, but it must be done. We didn't do.
All right, thanks. I'm going to take a few more here. And again, if we don't get to your question now, we'll send you an email. So this person says, thank you for this interesting presentation. Will it become possible to modelize optical components that have fabrication errors, for example, surface irregularities? Thank you.
And we are very close to the scattering problem. So I would say yes. We have diffusers. We have a quite interesting concept from a quite very beginning. If you talk about scattering of surfaces, or from lens systems, or if you talk about irregularities, then we need to separate the effect of the irregularity and the effect of the nominal surface. And we have a so-called stack concept. That means we have a concept that we put on a surface a stack. The stack can, for example, include this error, this kind of irregularity in the surface. And the good news is the modeling of the surface and the modeling of the irregularity are separated. So we can separate the two effects. It means what we do here is we have the regular thing, and then we would start an additional perturbation by the irregularity to propagate as a second coherent, mutually coherent mode. And so that is definitely something we can do. We, as a software maker, of course, always need cooperation with some people who give us a specific problem to test that. We are not an optical engineering company. We are a software company. So I can see how to do that, but it should be done in a project together, and then we can show how to do that. Yeah.
All right. Well, that's all I have time for now, but I do want to close on not a question, but a comment. Someone says an enlightening talk. Thank you. I am seeing some other thank you notes as well. So it's a good segue into this note. If you think of another question or you have another comment for us or for Frank, go ahead and email us at webinar@photonics.com. That's webinar@photonics.com. You can also email us to request a copy of today's slides. So this whole session was recorded. Once more, you will be able to see that online within a few days. You will not have to hunt for it. You're going to get that in your email inbox. And thanks for attending. I would like to thank our presenter one more time. You just heard from Frank Wyrowski of LightTrans. And thank you everyone for attending Next Generation Optics Software, Trends in Technology. This webinar again is sponsored by LightTrans and hosted by Photonics Media. We'll see you later.